Physics Part 343. We've got an example for you. It is required to select charged ions which have a speed of 4.2 into 10 power raised to 6 minute per second. The electric field strength in the velocity selector is 3.2 into 10 power raised to 4 Vm. Calculate the magnetic field strength required. Now it's your turn. Singly charged ions pass undeviated through a velocity selector. I beg your pardon. Singly charged ions pass undeviated through a velocity selector. The electric field strength in the selector is 3.6 into 10 power raised to 4 Vm. And the magnetic flux density is 8.5 beta mt. Calculate the selected speed of the ions. The Hall effect. What is the Hall effect? Consider a thin slice of a conductor which is normal to a magnetic field. As illustrated in the figure, when there is a current in the conductor in the direction shown, charge carriers, electrons in metals, will be moving at right angles to the magnetic field. They will experience a force which will tend to make them move to one side of the conductor. A potential difference known as the Hall voltage VH will develop across the conductor. The Hall voltage does not increase indefinitely but reaches a constant value when the force on the charge carrier due to the magnetic field is equal to the force due to the electric field set up as a result of the Hall voltage. The size of the Hall voltage depends on the material of the conductor. The current in the sample and magnetic flux density, if the current is kept constant, and then the Hall voltage across the sample will be proportional to the magnetic flux density. The Hall effect provides a means by which flux densities may be measured using a Hall probe. In general, the material used for a Hall probe is semiconductor. This gives a Hall voltage many thousands of times greater than that of a metal under the same conditions. Comparing the effects of the fields, we can summarize the effects of different sorts of fields on masses, charges, and current carrying conductors. Although, as we have seen, there are close analogies between gravitational and electric fields, there are some ways in which they behave very differently. Start with the effect of gravitational field on a mass, because masses always attract each other. A mass placed in the gravitational field will always move in the direction of the field from a position of higher potential to a lower potential. For a field produced by a point mass, the field strength obeys an inverse square law relationship, and the potential obeys a reciprocal relationship with distance from the source of the field. Electric fields are like gravitational fields in that for a field produced by a point charge, the field strength is also given by the inverse square law and the potential by a reciprocal relationship. However, we can have both positive charges and negative charges. A positive electric charge moves in the direction of the field from a position of higher potential to a lower potential, just like a mass in gravitational field. But a negative charge does just the opposite.